Hello students, welcome to this video. What we are doing here, we had this Laplace transformation, and then we had some property of that Laplace transformation, and then we have seen that we have convolution theorem which can make taking Laplace inverse transform easier at some places. Now you see we had this first shifting property. Already we have discussed this. First shifting property was that if you have L of f of x is say capital F of s, then if you multiply on left hand side with e raised to power ax, then on the right hand side s will be replaced by s minus a. This we have already done, right? Okay. Now I'll also tell you what else we have done. We have done that if you have if you multiply here with you multiply f of x with x, then you see that you have to on the right hand side you had to take the derivative, right? This is what also we had done, and then we had taken that okay, what happens if we take the derivative here? Then we have seen that on the right hand side you have to multiply with s, right? S f of s minus f dash minus f of 0. So it was like this. Okay, here also you see now we have multiplied with e raised to power ax, and we saw that on the right hand side we have s minus a. Now our question in our mind is, what will happen if we try to find out something like f of x minus a, that in place of, here you see on the right hand side s is replaced with s minus a. So what happens if we know L of f of x already, and we want to know what is this if I replace my x with x minus a? Okay, to the answer to this question lies in second shifting theorem, and we'll see that not exactly this term will appear when we'll see the second shifting theorem, but something like this will appear, and that will answer our things. So that is the idea of why we are going towards second shifting theorem. Okay, now before I write the statement for second shifting theorem, I need some background, so I'm doing that right now. So the first thing which we need is called a unit step function, right? So let us see, this function sometimes is also called Heaviside function. So let us see what is a unit step function. A unit step function is just simply a ux is defined as, sometimes it is written as hx, but we'll use this notation, is defined as 0 for x less than 0, and it is 1 for x greater than or equal to 0. So if you draw the graph, so you have 0 here, right, and your function looks like that. It is 0 everywhere on the left of the axis, and then at 0 it is 1. So you have an open dot here, and this distance is 1, and you have a closed dot here, and then here. This is the graph of a unit step function. And if we talk about say u of x minus 1, then it means that this graph will be shifted to right by 1. It means that, you see, then you will have this thing that at 1 you have the discontinuity. Here is this jump discontinuity at 0, right? Now at 1 your function will be 0 everywhere before 1, because this is how u of x minus a, you are saying u of x is 0 for x less than or equal to 0, less than 0. So u of x minus 1 will be 0 for x minus 1 less than 0, that is for x less than 1, and it is non-zero, and it is equal to 1 for x minus 1 greater than or equal to 0, that is for x greater than or equal to 1. So that is why your point of discontinuity will be shifted to 1 for when you replace x with x minus 1. So your graph will look like you have this jump discontinuity at the point 1, right? And similarly, if you have u of x minus a, then it means that your jump discontinuity is at the point a can be negative or positive, whatever is at a, right? And this is equal to 0 for x less than a, and it is 1 for x greater than or equal to a, right? So if we draw the graph of a unit step function, we write it as uax, right? So this will be at a, you have this discontinuity, so your graph looks like this, right? Here it should be an open, let me very clearly, this should be an open dot. It means that this point is not included. So this is the graph of the unit step function UAX, having this A represents the point of discontinuity, right? Fine. Okay, so now suppose you have a function g of x. Suppose you have a function g of x is equal to x square, right? And you multiply this function, say u2x. Now can you think what will happen? You see, if you multiply your function x square with u2x, this is the new function, this is x square ux minus 2, right? So this is x square into, this function is 0 for x less than 2 and 1 for x greater than equal to 2. So your function becomes 0 for x less than 2 and x square for x greater than equal to 2, right? So if you multiply gx with the unit step function, so this is what you are going to get. So basically, for any function fx, if you multiply it with uax, you will get it as 0 for x less than a, and it will be f of x for x greater than equal to a. So this is important to note. And conversely, suppose you are given this function. Suppose you have a function f of x which is defined as f1x for x less than a and f2x for x greater than equal to a. So the question is, can we write this function in terms of unit step functions, right? Functions. So you see, you think about it. Let us draw the graph first, then we will have an idea. Okay, I'm just making right, I don't want this. This is my point A here, right? My function is on the left side of A, this is f of x, f1x, right? Some graph, this is not constant, so this is f1x, and on the right at A and on the right hand side of A it is f2x. So this is what I have. Fine. Okay, now I want to write it in terms of unit step function. So can you if I can write this as, I can write this function as f1x plus f2x minus f1x into uax, right? How that we'll see just now. You see, here I'm saying that take everywhere f1x, right? It means that here also I'm taking f1x, whatever is the function, and then okay, I'm making fine. Okay, and then what you're doing, you have this here uax, this is 0 for x less than a, this quantity is 0 for x less than a. So you see, if you open this function, what you will get f1x plus 0 for x less than a, and this will be f1x plus f2x minus f1x for x greater than equal to a. So this f1 and f1 will cancel and you will get your function back, right? So whatever was the original. So whenever you have a function like this, f1x and f2x for x less than a, x greater than equal to a, you can write this function as f1x plus f2x minus f1x into uax, right? Now suppose you have a function which is 3 valued. This is important, I'll just show you how we will use it. Suppose you have another example that you have a function which is f1x for x less than a, and it is f2x for x greater than equal to a and less than b, and it is f3x for x greater than equal to b. How can we write this function in terms of unit step function? Write this function in terms of unit step function, right? So you see, I can write it as this: f1x plus f2x minus f1x into this point of discontinuity, that is uax, plus f3x minus f2x into ubx, right? So now you see, this is 0 for x less than a, right, and 1 for x greater than equal to a, and this is 0 for x less than b and 1 for x greater than equal to b. So what will happen if you expand it? You see, for x less than a, this is 0 because x is less than a, and also this is 0 because obviously if we are writing this function like this, so you have this situation: a is here, b is here. So if x is less than a, for sure this is less than b also. So you will get, when x is less than a, you have f1x, and these two terms are 0. Fine. Okay, now when x is greater than equal to a but less than b, in that case this is 0, okay, because your x is still less than b, but this is 1, so you will get f1 plus f2 minus f1, so that will be equal to f2, right? And when your x is greater than b, so you will get, this is also 1, this is also 1, right? So you will get f1 plus f2 minus f1 plus f3 minus f2. So this will cancel, this will cancel, so you'll get f3. So you see, you get your function back. So this is how you can write your functions in terms of unit step function. Let me give one more example. If you have 4 values, so you have f1, f2, f3, f4 for x less than a, this is a less than x less than b, this is b less than x less than c, this is x greater than equal to c. In that case, you can write your function as f1, so you see idea is f1 plus f2 minus f1 into ua, that point of discontinuity, this is your unit step function, plus then go for next f3 minus f2 into the unit step function at the b point, plus f4 into unit step function at the c point, f4 minus f3 into unit step function at the c point, right? So if you have let us do one example. The example is, express the following function in terms of unit step function, right? So you have f of x is sine of x for x less than pi, this is sine 2x for pi less than equal to x less than 2 pi, and this is sine 3x for x greater than equal to 2 pi. Right, so this is quite simple. You can just write f of x as, I told you, f1x plus f2x minus f1x, that is sine 2x minus sine x into the function, unit step function at pi, right, plus f3 minus f2, that is sine 3x minus sine 2x into unit step function at the next point, that is 2 pi, right? So you can also write it as sine of x plus sine of 2x minus sine of x, u of x minus pi plus sine of 3x minus sine of 2x into u of x minus 2 pi, and you can further state where uax means this is 0 for x less than a and it is 1 for x greater than equal to a. So this is how we write a given function, which is a multi-valued function, in terms of unit step function. Now in the next video, I'll tell you what is the second shifting theorem statement, and then we'll see that how this. Thank you for watching our video. Please do share and subscribe, and also you can join our channel for paid membership. We have 3 plans, 59, 89 and 119, right? For this you have these 3 live sessions in a month, and for this you have 3 live sessions plus one video of your own choice. You can send us the topic, and we will create a video in a week and we will send you back, or we'll upload on our channel. And plus in this 119 you will have your own PDF notes for a particular playlist. You can go into the join button, you can click the button and you will have detailed information about that, right? And this money, this will not only help you, but it will also help us to create this quality mathematics content for everybody, right? So we are creating these videos for free, and we want that everybody should have a quality mathematics education. So whatever you are contributing, it is kind of donation also. It will be, it will help us in scaling up our channel for more videos, and we will try to cover as much as topics as possible. Thank you for your support. Please share this video and keep supporting. Thank you.